Okay, picking back up again on our pre-calculus exam debrief. We're up to problems 13. You'll note that 13, 14, and 15 are all quadratic equations to be solved. None say use the calculator, although we could have if we wanted to. You may have remembered earlier on I had mentioned there was a slide at the beginning about skills needed. And under quadratics, you see you should be able to solve quadratics by factoring, by completing the square, and by using the formula. So for this debrief, I'll go ahead and use those three techniques on these three problems. This first one, we'll go ahead and factor. We note we have x squared minus 6x plus 5, and it's supposed to be equal to 0. So this factors very nicely as x minus 1. X minus 5 is equal to 0. We'll use the zero product theorem. Because we have two factors whose product is 0, we can immediately say that x minus 1 must be 0, x is 1. Or we can have x minus 5 is equal to 0, x is equal to 5. Choice C. Okay, number 14. Once again, we have the same quadratic, x squared minus 6x plus 5. But this time it's supposed to be equal to 12. So I'll do this by completing the square. Remember, the technique involves moving the constant first. So I'll take this 5 and move it to the other side. 12, take away 5. So we have x squared minus 6x is equal to 7. And then I'll complete the square. The way we complete the square is, again, we take half of this coefficient here. Half of negative 6 is negative 3, and negative 3 squared is a positive 9. We'll add that to both sides, positive 9. The left side is now a perfect square. We could write as x minus 3 quantity squared, and the right side is 16. And we finish this problem by taking the square root of both sides. Now, one of the techniques in this completing the square, right, remember you have to do both plus and minus the square root of both sides. We don't need to put it on both sides, but we do have to put it on one side. So here we go. We'll take the square root of the left, x minus 3, and then plus or minus the square root of 16. Note the right side cleans up very nicely, plus or minus 4. And on the just a second here. Okay. So we'll go ahead and move the 3 over to here, and we finish with x is equal to 3 plus or minus 4. Both of those clean up very nicely. X is equal to 7, or x is equal to negative 1. 7, negative 1, choice B. Okay, and for problem 15, we again have the same quadratic. This time it equals 2. So we have x squared minus 6x plus 5 is equal to 2. The quadratic formula does require the right side to be 0. Remember, it started if ax squared plus bx plus c equals 0, then we can say what x is. So let's subtract 2 from both sides. Is equal to 0. This does not factor, so we could not solve it by factoring. We could solve it by completing the square, but we said we would solve this by the quadratic formula. Note that the a is the coefficient of x. The b is the coefficient of x squared. B is the coefficient of x. And c would be the constant, which is 3. That's our a, b, and c. And the quadratic formula says we can write down x is equal to the opposite of b, which is a positive 6, plus or minus the square root of b squared, which is 36, right? Negative 6 times negative 6, minus 4 times a times c. Okay, and all that's over 2 times a. So there's our answer. We should clean it up because notice that the choices are all with the radical cleaned up a little bit. So this will be 6 plus or minus the square root. What do we have? 36 less 12. all over 2. Or if we clean it up a little bit, 36 less 12 is 24. So 6 plus or minus square root of 24 over 2. And that is choice A. Right? So here we have a negative 6, which is wrong. And these other ones have 48 under the radical, which is not right. These are real numbers, right? We could estimate these pretty easily, I suppose. We know that the square root of 24 is about 5. So if we did 6 plus or minus 5 over 2, about 11 halves and about 1 half. So those are real numbers, right? They're on the number line. They're both positive. And because we had mentioned completing the square, I guess it wouldn't hurt to do this by completing the square as well. Many people find it quicker than using the quadratic formula. So if we wanted to solve this same quadratic by completing the square, here's how it would go. We have x squared minus 6x plus 3 is 0. Okay, so we move the 3 across. X squared minus 6x is equal to negative 3. We complete the square just as we did in the previous one. Half of negative 6 is negative 3. Squared is plus 9. We add that to both sides. And we now have a perfect square on the left side. X minus 3 quantity squared. On the right side, we have 6. Right, so we take the square root of both sides. Remember to do plus or minus on the right. Plus or minus the square root of 6. Lastly, to get the x, you chuck the 3 in here. So x is equal to 3 plus or minus the square root of 6. And you might want to wonder, does that really mean the same thing as what we had before? If you recall, the answer, the choice that we had was this 6 plus or minus square root of 24 over 2. So we're sort of pushing it against this, 6 plus minus root 24 over 2. And we can do two things. First of all, we'll split this up, 6 over 2, square root of 24 over 2. And sure enough, the 6 over 2, that's the 3. And root 24, you can find the perfect square in there, right? That's 24 is 4 times 6. Right? 24 is 4 times 6. So the square root of 24 is 2. So this part here can clean up as 2 square roots of 6 over 2. 2's cancel, and there's your square root of 6. So yeah, either one would have worked fine. Okay, number 16. This is function notation. Once again, we're dealing with the same function, right? F of x from the previous problem was x squared minus 6x plus 5. X squared minus 6x plus 5. And that's going to go at the back end here. So we got to subtract that away. But in front of that, we need to figure out what f of x plus h is. Well, how this function works, of course, is whatever the input is, f of, say we had pi as a, for instance, we would put it into where the x is, and we would get pi squared minus 6 pi plus 5. Well, we don't care about f of pi. If we had f of stuff, whatever that stuff might be, the rule says to take whatever the stuff is, whatever the input is, and to square it, and then take away 6 of those stuffs, and then lastly add 5. That's how this particular function f works. Well, using that analogy, this x plus h is just some stuff. So treat it just like you would this sort of goofy way of writing the input. So f of x plus h is going to be x plus h quantity squared minus 6 times x plus h, and then plus 5. And unfortunately, that's not one of the choices, so we're expected to clean this up a little bit. And I would hope that expanding that binomial as a square is pretty simple for most. Right? X squared plus 2xh plus h squared. Here we have to distribute that. So we get minus 6x minus h, minus 6h, right? Minus 6h plus 5. Okay, so this entire expression here would fit in right here. Okay, so we figured out what f of x plus h is. The problem was to take f of x plus h and then subtract off f of x. Well, we've got the f of x plus h there in the box. Let's see if we can move this around here. There's my box. There's part of it. And here's some more. It's coming. Okay, so we have f of x plus h, and now we have to take away, subtract off, f of x. And f of x, if you recall, was this right here. So let me see if we can just drag that down here. Aren't smartboards nice? Now the key, and then probably where you may have made an error, you have to subtract off all of that. So that minus sign needs to distribute when you do the subtraction. So cleaning things up a bit, we have x squared plus 2xh plus h squared minus 6x minus 6h plus 5 minus x squared positive 6x, right, because we're distributing this minus sign, and then minus 5. And then you'll notice that the 5's go away, the x squares go away, and the 6x's also go out. 6x and 6x. Okay, so what you're left with is the 2xh and an h squared and a minus 6h. Okay, so 2xh plus h squared minus 6h. Answer was B. The next problem asked you to work with this and to divide it by h, right? So the next problem was find what you had at the beginning. You might want to use the answer you had and then divide it by h. So if I just go back to our previous one here, this is our final answer here. And if we divide this by h, that should give us the answer to the next question. F of x plus h, take away f of x over h. And the way you would do that, of course, is to factor the h out of the numerator so you can cancel it. 2x plus h, take away 6, divided by h, once you can cancel those common factors. So the answer to this next problem would be 2x plus h minus 6. 2x plus h minus 6. 2x plus h minus 6, yeah. This is a corrected version. You might recall that on exam day that choice wasn't there and you were directed just to write down the correct answer as choice F. So 2x plus h, take away 6. Okay, so sorry about not proofing the exam the first go round, but that's how you do it. Okay, 18 and 19, we have this function, x squared plus 5x minus 6. Note that this is not the same quadratic as we had before, right? So just note we're dealing with a slightly different function here. X squared plus 5x minus 6. And it says the graph of f is a continuous line with no holes or breaks. And it talks about the intermediate value theorem. It says, so maybe we can draw a little picture here quickly, just to sort of get a sense of what's going on. When x is 2, f is 8, that gives us that dot. And when f is 4, f is 30. So that's up there. It says we have a continuous line. In fact, this is a parabola. We could actually figure out what the shape of the parabola was if we wanted. But between these two dots, we do have a continuous line with no holes or breaks. And the intermediate value theorem says f, this is the y-axis, if you will, or the f-axis. It's interesting, there really is no y in this problem. If you look at that, all it has is x's and f of x's. So technically, this is the f of x axis going vertically here. But we note that the intermediate value theorem says f must attain all values between 8 and 30. So every number between 8 and 30 has to be achieved somewhere on the interval between 2 and 4. If you think sort of the moving dot idea, so here's the dot. If the dot is at this location, and as x goes from 2 to 4, this dot's going to run up the line. Because there's no breaks or holes, the y-coordinates have to be all of the numbers between 8 and 30, all the intermediate values. That's why this is called the intermediate value theorem. Sure enough, as the dot goes up, all those y values are achieved. Okay, fine. Then it says, find f of 3. Well, 3 is one of the numbers in this interval. There's 3. So we know that the y value has to be, if this is 3, the y value has to be some number between 8 and 30. Has to be. And it just says, what is f of 3? So not hard. F of x, x squared plus 5x minus 6. And so f of 3 is 9 plus 15 minus 6. What's that? 24 less 6 is 18. Okay. Now, why all the rigmarole about the intermediate value theorem? Because this next problem, again, addresses the intermediate value theorem. So let's see, get a little picture going. It says a sketch would help. So I think, smart idea. If it says draw a sketch, you should probably draw a sketch. So here's the x-axis, and here's the f of x-axis again, or the y-axis, if you will. I mean, if we said y was equal to f of x, which was equal to x squared, and I forget the linear term, 5x plus 6, plus 5x minus 6, like that. If that was that, then we could call this y-axis or f-axis. But at any rate, it says f of negative 7 is 8. So 1, 2, 3, 4, 5, 6, 7. Here's negative 7. 1, 2, 3, 4, 5, 6, 7, 8. Here's 8. We have a dot there. And f of negative 4, 1, 2, 3, 1, 2, 3. There's negative 4. F of negative 4 is down here at negative 10. Just extend my picture a little bit. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Negative 10. And so we have a dot there. And again, because this is a continuous line with no breaks or holes, and in fact it's part of a parabola, we have this curve that looks something like this. If I can draw a curve, it's a piece of a parabola. And again, if you think about these as two endpoints of a continuous line, as a dot would travel, say, from this x value, which is negative 7, right, as it travels down the parabola to negative 4, the y values all have to go between 8 and negative 10. Every single y value intermediate between these two has got to be achieved. You can't get from the dot up here to the dot down here without going through every single y value between 8 and 10. Okay, so the directions say, which of the following statements is not true? This first one says f has to have a 0 somewhere between negative 7 and 4. Sure enough, if we have to cross the x-axis somewhere between negative 7 and negative 4. Remember, zeros of a function are synonymous with the x-intercepts of the graph. Okay, so that's true. How about this one? F of x must equal 10 somewhere between the interval negative 7 to 4. Well, 10 is up here, right? 10 is above 8. So do we have to get up that high? No, that's a false statement. In fact, that is going to be the answer to this question. Let's check the other three. F of x must equal negative 10 somewhere. Sure enough, and in fact, it occurs all the way at the right endpoint, right? So at the right endpoint, at negative 4, we know that f of x is equal to negative 10. In fact, we were told that as part of the prompt. Yeah, duh. So that's obviously true. F of x must equal 1 somewhere on the interval. Sure enough, it happens to occur just to the left of the 0, right? So we go up here, and somewhere around there, you can imagine there's a y-coordinate of 1. We have to get to 1 because 1 is between 8 and negative 10. So that one's true. And the last one says f of x must equal 7. Sure enough, 7 is up here somewhere, right? So here's 7. and the point has got to have a y-coordinate of 7. I drag that up there. So that's also true. So the only one that's false would be this guy right here, and that is the answer to that question. Okay, we've been going on 20 minutes here. Let me go ahead and stop this video here. Intermediate value theorem is important in calculus. With these two exam questions sort of address the intermediate value theorem.